So let's begin. And I begin by presenting the hosts of this webinar today. And as you can hear, we are conducting it in English as we have English-speaking participants as well. So on my virtual left, I have Agerkrantz, who is the founder of Agerkrantz Controls, who we have used in several projects, and he will present his sensor solutions. And on my right, I have Katiben from Agerkrantz, which we also have used in several occasions during different projects, and he will also give a brief introduction to Agerkrantz. And on my virtual left, I have Michael, who is the Beacon Tower product owner. And my name is Jakob Abel, and I'm the managing partner of Glaze here in Denmark, and I will present Glaze and Beacon Tower. And just in general, with this webinar, we have reserved some time in the end where you can ask questions. So please note them down if you have any questions during the webinar, and we'll try to answer them in the end. All right. So before we move further into detail about Beacon Tower and the different projects that we wish to introduce to you, we'll just delve a little bit into what Glaze is as a company. And Glaze is a company that have developed and own Beacon Tower. And just a very brief introduction to Glaze. Our focus has from the get-go been on bridging the gap between OT, connected products, and business IT. That is more or less the value proposition and what we have been doing for several years. Glaze was founded in 2015. And we have done a lot of projects, and we have delivered projects end-to-end and customized projects as well. And all these projects have led into the design and the guiding principles that we have used to design Beacon Tower with. And very briefly introduced, these principles are that we should be able to start small and cost efficient with Beacon Tower. We should be able to scale with the needs of our customers. And that is not needs only in terms of data, it's also in terms of different data sources that we wish to connect to Beacon Tower, being it sensors, being it machines, being it different SCADA systems, or even being it different external data sources. It's also scale in terms of how we wish to work with the data as customers and as stakeholders. So what is also very important is that we have a platform that can actually be used in many different ways during the lifetime of such a platform. And further on, we have focused on the ownership of data, where data resides, who owns the data, and who can control the platform. Also a very important point when using an IoT platform. And lastly, what we have focused on is to achieve an open architecture with open data models so that external actors, internal actors have complete flexibility for all types of applications, and that they can integrate to the platform in a very straightforward way. So that's the general introduction to Glaze and to what Beacon Tower is. And if we just delve a little bit more into detail of Beacon Tower, we have in this slide tried to sum it up, what the general use cases are that exemplifies how Beacon Tower can be used, and the capabilities that are general properties that make Beacon Tower a strategic platform for the long term. And if we look at the use cases, so the general use cases are from the top, that you are able to organize your data as in an asset-driven way. So that means that you can organize the data after your operation, after your business, after your customers, in short, after all the sort of assets and all the ways that you want to structure your data in. So that means that not only can you stream data in and handle the different input data and different data sources, but you can also structure it in many different ways. And you can also make rules and dashboards on top of these assets that you define on these live data that are streaming into the platform. And that leads us to the second use case, which is that you can now make advanced condition monitoring. So since you can actually structure the underlying real-time and machine data the way you like, in as many ways as you want to, that means that you can now also apply these rules, these dashboards, on top of these new structures. So that is a way to do advanced condition monitoring. So for instance, you can structure, you can aggregate data from a lot of underlying devices into one asset, and then have more general rules applied on these data that are streaming real time into these underlying devices, but also into the more general aggregated asset, which is also being monitored real time. And then the real-time rules will sometimes be triggered, and then they can notify internal actors, that being it persons or being applications, or external actors if that is needed, being customers or service partners or other actors that you are required to act on these data. What is also very important about Beacon Tower is that you can customize it completely, so it's not only an how do you say it, a commercial off-the-shelf kind of product. It's also a customizable platform that you can completely integrate and customize to your needs. And that is able to do so because it's an open architecture, and it's also done in a way so that you can actually integrate to the data and change the user interface as you like it. And you can also have the whole platform running in your cloud platform. And it all leads down to a more general use case, which means that you can now achieve effective AI projects, machine learning projects, because you can reuse all these data models, all these structures in Beacon Tower in your AI projects. And that also means that you can start to automate processes, since you can do these advanced condition monitoring and rules triggerings on your data structure, so that you can now start to automate the processes, so that these rules trigger notifications that triggers different actions in other applications, for instance. And if you just briefly zoom into the capabilities of Beacon Tower, that means that instead of you having to develop such a platform that handles all these different sorts of problems that arise when you work with many different sensors or machines or SCADA systems or even external data sources, it lets you now focus on your domain, on your business, and that you can start to use your time on those kind of projects instead of developing an IT infrastructure for this. And Beacon Tower is a service, so that means that we will continually update it, we will continually monitor it, and we continually extend the functionality of Beacon Tower. Also, general capability of Beacon Tower is that it's possible to deliver it in your cloud tenant, which means that we can run it, Beacon Tower, as a dedicated tenant, as a dedicated instance in your tenant, meaning that you have 100% control of the data and the platform. It's only running for you, and all the databases and all the Azure resources are only running for your dedicated needs. And it also means that it's a repeatable platform, so that you can have many instances of Beacon Tower in your Azure tenants, or in our, if you wish us to take care of that. But that means that, for instance, if you want to have a test environment, or you need to have an environment that is only specifically handling data for one customer, then that is also possible. And since it's an open architecture, open data models, We have APIs to almost everything in the platform, and everything is white box. So it's not a hidden. It's not something that we try to hide how we have implemented it. That means that it's quite easy for others to build applications that integrate to Beacon Tower, and it's actually also quite easy to make configurations and customizations on top of Beacon Tower, meaning that you can use your own IT department or you can use other partners if you wish to. You can, of course, also use our consultant teams that can assist on site, and we can also develop it with our offshore teams where we have very cost-effective prices as well. So that was the brief introduction to Beacon Tower. Now, what we would like to do in this webinar is to introduce the hydrostate sensors from Agerkrantz, and after that, SIA Connect, since they are quite integral components in our utility projects that we will, after those introductions, try to present. So having said that, I will now pass the word to you, Alan.
Yes, thank you, Jacob, and hello, everybody. Yeah, we have developed a solution to monitorize data from district heating grids, and I think, and I hope we have a page more. Okay. The thing is, there's a lot of potential savings in district heating. So before we can do the savings, it's necessary to have the measurements, and the measurements we need is pressure, temperature, and also flow. And what we are working with is in two steps in district heating. We have in the grid we are measuring pressure. If we look here in the section valves, which are valves that is on the main grid and into sections, and we are measuring temperature and pressure in there. And when we do that, then we have the possibility to control the main pumps and lower the pressure just to the accurate pressure, so we don't have more pressure than is needed. And by that, there is a lot of savings. We can reduce. We can find up to 20% savings by year to have the accurate pressure. And when we're lowering the pressure, we also reduce leaks in pipes, and we also reduce pipe loss. And the other thing we can see is the bypass point. And it is so the pipes in district heating is dimensioned for winter, but in the summer times the pipe is too big, and if we don't have bypasses, then it will be there's two possibilities. We can do as we used to do, is to have a high temperature, but the future points the other direction. We are lowering the temperatures in district heating, so by that we need a bypass point. A bypass is bypassing temperature from water from the inlet pipe to the return pipe, and by this system we will have an motor valve that is automatic having an control the bypass. And this is our focus areas. And if we take the next slide, we can see our branch where we have a microcontroller which can control the bypass and also deliver data in real time. And we have a GPS antenna, so we can see where all the controllers are placed in the grid. And it's working by LTE-M, narrowband IoT. And there's a built-in antenna, and there's also an external antenna, so we can take the antenna outside of a well. We have 4 digital I2T inputs. We are using them to the pressure transmitters, which also are digital, and by that have low power consumption. And we have 2 analog inputs, 4 to 20 milliamps, and 1 analog output, 0 to 10 volts, so we can control other motors. And we have output for 24 volts step motor. Yeah, we're working.
Can I ask you a short question? Is it not so that you put a set point to your control box, and then it will control automatically the valve so that it's done locally once you have sent that?
You're totally right. Yeah, yes, we are sending a set point for the bypass, so it could be 60 degrees in the summer times, where we would like to have a bypass, and then the built-in microcontroller is have a PID regulation to adjust the motor valve to secure the 60 degrees. And the other way, in the winter times, we just need a frost protection, and then we will have 2 degrees instead of 5 degrees. So we can say that that's the first step. It's also possible to build in some AI functions to let it control by outdoor temperature instead, because we do, yeah, I can see there's both participants from Denmark and Sweden, and in both countries we don't have a specific border between summer and winter. We can have winter one week and summer next week, and then winter again. Or maybe the whole thing in one day. So it's the possibility to use AI for the regulation. Yeah, and we can say for our cooperation with you, Jakob, and Beacon Tower, it's easy to use, and by that also easy to instruct customers, and also the possibility to customize it for specific customers is a very good point.
Yes, all right. Thank you, Alan. And if you have any questions to Alan, please note them down, and then we'll go through them in the end. And then I will pass the word to you, Katiban.
Thank you, Jakob. I'll start with a excuse. I'm in an exhibition hall, and this is the most quiet place I could get. And I hope my headphones are actually reducing the noise. So, okay. Hello, guys. I'm representing SIA Connect, which is producing and selling industrial IoT gateway. We have been around since 2017 and located in Aarhus. So what I'm going to explain is a very unsexy device, but it is vital in all the communication we do from edge devices like sensors and into cloud services, as what Jakob is offering. But to understand it, I think I will, Jakob, if you could skip to the next slide. I will start somewhere else, and it's at your home. So most homes are equipped with a kind of router. So router is the home, the router you have at your home is pretty much similar to what we actually are doing. So the router is have 2 different jobs. It is actually connecting devices and distributing data to a phone, a computer, or TV, so you can access Netflix or TV2 or whatever you are actually doing at home. So the router has the ability to connect to a cloud, and it also has the ability to distribute data into the specific device that are requesting data. In the same way, the next slide, please. The same way the SIA Connect is acting. So SIA Connect is a kind of router just an industrial term, it's called the IoT gateway. It can connect to different sensors or devices. It could be something measuring electricity or water flow or temperature or whatever. In this case, we have with Alan is related to water pressure, and then we can take the signal, convert it, and send it to a cloud, which we're here in this case is a beacon tower. One of the things that is very difficult in this task is that the different sensors are actually speaking different languages. So what we are doing is actually converting the different language into one agreed language with beacon tower and send it to beacon tower. So Alan mentioned, for example, Modbus communication. That is typical for telemetry sensors, but it could also be 10 different other protocols that we have to convert. So what we are good at is taking different languages, converting them, and send it to an agreed language to the beacon tower cloud. One thing I would like to touch base on is security. I think most of the people here has attention to the security. We use for communication to beacon tower. We use MQTT, which is a very standard protocol for secure communication. And it has three advantages. First of all, it's port specific. So you only have, if you imagine a castle or fortress, and you have only one gate, you have to guard for any kind of attacks. So you cannot send MQTT to a random port. It is a port specific communication. The second thing is that it has an authentication. So it's very similar to the two-factor authentication you, for instance, have in your Microsoft 365 or whatever. So you have to provide something, and then you get something from the beacon tower cloud, and then you use that as an authentication. And finally, the data is encrypted, so it is a very secure way to communicate. So it is industrial standard. And finally, I would say we have done several projects with Jakob, and one of to mention a couple of them is Horsens Fjernvarme and Svanhøj, which is experts in critical handling or handling of critical liquids. And here you see some of the different protocols we convert from on the left side and into different cloud services on the right side. And as I remember, Jakob, your cloud is based on Azure, right?
Completely correct.
Okay. That was a brief presentation of Agerkrantz.
Yes, thank you. And we will move on. So, moving into the utility sector and starting to get a little bit more into that area, we have a slide here that we have not developed ourselves. It's done by the 4DH Research Center in Denmark, which is a research center that investigates the potential for developing solutions for the so-called fourth generation district heating. And the point of this slide is not to delve what is the definition of fourth generation district heating and so on. I guess most of you guys that are participating in this webinar has a good idea about what it is and how the utility sector is moving forward. The idea is to say that 4DH have said that there needs to be created synergies between three areas within district heating: grids and components, production and system integration, and planning and implementation. And one of their conclusions are that these requirements demand a flexible and open data warehouse platform that can allow numerous systems and devices to deliver and query consolidated data. And that is exactly what Beacon Tower is best at. So that's why it's very relevant to look into a platform like Beacon Tower if you're working within the utility sector, where we will see more and more differences in production mix and we will see more and more real-time data input coming from all sorts of different systems and sensors. And we need to have an overview of how to react to all these input. And this is also illustrated in this slide here, where we can see, generally it's just a representation, another representation of how Beacon Tower can be placed inside the utility sector, where we have a lot of different type of data streaming into the platform. That might be external data. It might be, in this case here, district heating zones, pumping station, or production OT, which all the data get processed, structured, and is integratable for other applications, whether it's inside Beacon Tower or whether it's outside of Beacon Tower, or even external for our installation and for our customer, so that external actors can work with the data. Now, moving further into detail and with some examples, we have Albertslund Forsyning as a case. We're currently working with Albertslund on this solutions. So this is the visions for the project, where we are currently good underway, I would say. And the technologies in this project are, we have differential pressure sensors from Hydrostate, that is Allen's sensors, and we're also testing some other sensors from a company called Intertech. We have meters from Deal, and we have connectivity through narrowband IoT, and then we're using Microsoft Azure as a cloud platform, where we have Beacon Tower installed, which is collecting all the data, of course. And then we have the gateway from Agerkrantz, which is sending the data from Beacon Tower to Albertslund SCADA systems. And the project is about to have data from different bypass cabinets, where we send the temperature and the differential pressure. I believe it's every 10 seconds. And the reason why we do this is that we want to locate, when I say we, it's of course Albertslund, that want to locate the points with the lowest pressures, the lowest differential pressures, in order to be able to optimize the main pump and the shunt pressures, so that we don't have too large a differential pressure or too low a differential pressure, so that we can continually monitor and then optimize the pump pressures. And why we do that is, of course, that if we optimize the pressures, then we can potentially save energy, because it might be so that we can actually lower the pressure. So that's one thing. And the other thing also, if we are able to lower the pressure, then we are actually also doing less stress on the pumps, and then you can actually save service, and you can save downtime, and you can make the lifetime of the pumps longer. By also having the real-time temperatures in the bypass cabinets, we can adjust the temperatures during winters in the bypass cabinets, as Allen has also touched upon. And we can also optimize the flow during summers, so that there is actually a flow going on in these subzones as needed. Further, we can now consolidate all these data from these sensors that are installed inside Albertslund in their net, and we can get the data into Beacon Tower, and then Beacon Tower can send these data to the SCADA through the Agerkrantz gateway, and then the SCADA can actually act real time upon these data, so that you get these measurement data, and then you have an adjustment routine in the SCADA that actually controls the different pumps through that SCADA system. And that can be the main pump. It can also be the pump, the shunt pumps that they have installed different places in their pipe network. Another thing is that they also wish to get data from their surplus heat producers. They have a data center that is producing surplus heat, and they also have other actors for instance, supermarkets, that they wish to receive measurement data from, in order to send these data to their cooperation partner called VEX, Vestegnens Kraft-Varme-Selskab, where they today do not get data about what the production of surplus heat is. And by having all these data sent into Beacon Tower can now relay that information to VEX, and VEX can now take into account what the surplus heat production is in order to optimize their production. So that's a case of Albertslund. And then we have the RACE project that we're also currently doing, which is an EUDP-backed project that we're conducting with Agerkrantz Controls, Aalborg University, Develco, and Energy Cluster Denmark. And the title is Real-Time AI Computing in the Energy Sector. And what we're trying to achieve in this project is that by getting data from the pipe network and getting data from the differential pressure sensors and temperature sensors that we get when we install Agerkrantz's sensors, the hydrostate sensors, and also getting the historical data from their SCADA systems regarding heat production and pressure and all the needed configurations. We can send that to the cloud, where we develop a machine learning algorithm that takes all this data into the physical model of the pipe network. And then we introduce also the historical and real-time energy prices and the historical weather data and the real-time weather forecasts in order to be able to make an AI-based real-time control of the current heat production and control the pump pressures, but also to be able to control the dynamically valves and then the pressures inside the pipes based on this AI model that, as I said, has developed this algorithm based on the historical data, but now also takes into account the real-time data in order to control the different real-time actuators. And this is a project going on as we speak. And here we have a short way of introducing how the actual flow is in a more, should we say, pseudo-code way of the AI. And what it also gives is it gives a way for, sorry, I forgot to say that it's done on Brønderslev Forsyning as a real case demonstration site. And what they get is they get a reduced power consumption of the pumps, as I always also introduced with Albertslund. They also get a reduced heat loss from the grid pipes, since they can probably be able to lower their supply temperature and also the return temperature. So that means that they can also, besides that energy optimization, they can actually also reduce the heat loss, and that means they also get a higher efficiency at the boilers and the heat pumps. And this is done, the whole solution is developed in an open source way so that others can contribute to the project, but it's also done in a general way. So it's of course not something that is unique to Brønderslev Forsyning. What we will do is we will make a way to model, in this case, district heating networks that then are able to be applicated in other areas and for other district heating companies without having to have it as a science project, but have it as a quite easy installation project that can be applied to new areas. And so this is some cases that we are currently working within, where we are using real-time sensors, we're using AI, we're using Beacon Tower, we are using SIA Connect to integrate to different SCADA systems, and we're also using Beacon Tower to update and control these sensors. And now we will try to demonstrate a little bit of how that can be done in Beacon Tower, so that you also see it in real life. So having said that, I will now pass the word to you, Michael.
Thank you, Jacob. Yeah, so let me share my screen here. So, so as Jacob said, we will show you parts of this solution. I mean, some parts are done and integrated for Albertslund, and some parts we are working on integrating. But as that is, I mean, that data is not ours. It's Albertslund, of course. We're looking at this in our demo environment. And therefore, we're using a range of simulator devices to be able to put multiple devices in here, as you'll see. So if you see some data that it will act very similarly to the real device and it connects to beacon tower the same way. But if you see some data that you wouldn't recognize in a real scenario, it's because it's simulated data simply for demo and test purposes. So to bring into this quickly, I will just first go through a bit on how beacon tower is built, and so you understand what we're looking at, and then we'll go into some of the specific things Jacob mentioned. First of all, so this is in beacon tower we're working with what we call assets. Assets can be a representation of a physical device. But assets can also, which we'll cover a bit, be a combination of other assets, or it can be a subset of one asset, or it's a way to reconstruct your view of the real world in the way that maybe the devices that send data that doesn't really represent. And we will only touch a bit on what those capabilities are today, and there are more things we can do with that setup. What we just looking at basically here is that we're looking at what we call a node tree, which is the district heating tree. Simply for this demo, a tree is simply a hierarchical way of organizing assets. You can have multiple trees, and this is just one way of simply finding the assets that we need to look at for the demo today. And then to the right, we have what we call well, we had a view of a specific asset, and in this case, that's a dashboard. Actually, we'll move to this one. It's a dashboard showing data, and it's a dashboard that customers can set up themselves. And you can have more than one. You have multiple dashboards, and so on. That's the basic view. And then if we go back a bit and look at so what we're now trying to do in both of these cases, pretty much for both Albertslund and Race. So the basics here is, of course, that we're gathering sensor data from these sensors out in the utility network. The way that we define this, the way we do this in the easiest way in beacon tower, not the only one, is that we make use of the Azure IT Hub, which is just a gateway to connect devices to very easily into the cloud and into beacon tower. And what we need to do, the only thing we actually need to do, so if there is a device that is IoT capable, or IoT Azure IoT Hub capable, the only thing we need to do is to define that asset or device in beacon tower. And we do that by creating a model, and that model contains the telemetry, the properties, and the commands that device supports. And as soon as that's done, that's all that's necessary to actually connect the device into beacon tower. And the next step is that you use this model. You can see it as a template to create an instance for a specific device, and that instance then it's like a one-to-one representation of that device, and it gets all the telemetry and everything, and it has those properties and commands that that allows you to control it if that's available. There are also, and we can quickly cover that. So if, for example, what Jacob mentioned before, there are other there are other types of ways of getting data in the beacon tower. The IT hub is one often used, but for example, in this specific case, we'll also be using CSV files as a way to get telemetry data into beacon tower, and we can also connect to REST APIs and well, pretty much any kind of integration that we would need, which would also feed data into one of these assets and one of these models, but you would just have multiple different ways of connecting to it. So the first step in this, and here we have the hydrostate device as an example. That is that we're collecting the data. You can first see that so the data is coming straightforward. Just this is a pure representation of the model that you saw. So it's all the data coming in here continuously. Then we set up just an example dashboard for this, which shows the real-time values, but also graphs and the location as this device reports location. So this is just one way of representing data. You can do it any way you like, but this is an example of how it's done here. So this is one type of device, and the benefit with it, of course, with Beacon Tower is that we are to a large extent we're hardware agnostic in the sense of that we don't sell our own hardware, and in this case we all have partnerships with Agerkrantz and CA Connect, and there are more devices connected in these projects. And so then we have the example of Insatec, which is another meter or sensor that we're also getting data from. And here, what I want to show here is an example of where we're having different data coming from two different types of devices. So while, I mean, you can briefly see that there's some different data here. It's pretty much the same. We do know both have flow and return temperature and pressure. And the idea here is then that this is data coming from multiple different sources, but from my perspective, from our perspective, we don't want to see it as different. We don't care as different devices. That might just be, I mean, a procurement decision or something like that. For us, it's just meters looking at pressure and flow and temperature data. And one way we can then use this asset hierarchy that I mentioned is that. And I will actually just quickly switch to PowerPoint to present that idea a bit more clearly. So what we're doing here, so this is a representation of factory machines, but it has the exact same setup pretty much. So in this example, we have two machines. They're two different types. They might have different telemetry values. They might have different names of those telemetry values. So they would talk to the IoT hub as two different types of devices. Once the data comes into Beacon Tower, yes, we have one model for one of them, which is one asset, and we have another model for another one because they might be slightly different. But we still have temperature in both of these, and we have, in this case, RPMs, which is just another telemetry value, which are also not seen as the same because they are different. They're in different models, but we know they are the same. So what we do is that we create a normalized asset model, and this means that we have there one temperature value and one RPM value, and then we create bindings between these. And in those bindings, you can, if you want, transform values. For example, if one device delivers Fahrenheit and one Celsius, we can choose here to only have Celsius in both. And sometimes we only do this to have one type of asset in Beacon Tower, so we don't have to look at them in different ways. The next part you can do with this. So once you've done this, you can also use the asset hierarchy to create a structure. In this example, we put this in as a machine, and then we combine that with other machine assets into a production line and then into a factory. In this case, that can be done in heat production settings, but it can also be used in utility networks if you want to represent that network as different layers of assets. That has some value sometimes you don't need to, but that's usually a discussion to find the best way to use this. If we go back here, so I want to show you this setup. So what we've done here is actually that we did exactly this. So we have these 7 different sensors of that look different. And now in this one, we have this common normalized asset, and that is actually what we're interested in looking at. So while we have these, like from a technical standpoint, they are here, they are the one-to-one representation of what's actually coming in. This is probably the ones that we're going to work with continuously, because that they provide the data we want. And that also makes some things easier, because now we can more easily compare data between them, because now they are in one asset, and we can like plot all that data in a chart or something like that. And also in this case, I can show you, for example, if we move from the asset itself and into one of these tree nodes, now we have this high-level overview of these different assets, where they are located, and we can get the data from them, and now they are seen as having the same type of data. The last thing we can cover a bit here, a couple of different, capabilities that you have. For example, we in Beacon Tower we can manage alarms. So it's basically when a telemetry value is outside of a certain threshold, we get an alarm here. Sometimes you choose to manage that outside in other systems, so we only send all our telemetry data out. And sometimes you want to handle it here to get an indication of something being wrong. Depends on the setup and what other systems you have around it. In this case, here we had a pressure alarm saying that the pressure between flow and return was too low. And we can see when it happened during the morning. And there's an example here. If we just then actually look at the pressure as the pressure differences for a couple of devices, we see one here that goes falls quite low, and that can be an indication that that's something we want to look further on. So this is just a charting tool where you can do like a first level of analyze, unless you have, of course, just pushing all the data into a more advanced analytics tool. You can do that outside also, or both, depending on what you're looking for. The other part where we are not there yet in this project, but that's something that's in the scope and that we are looking at. One is of course to take this data, as Jacob mentioned, and push into the SCADA system. We can pretty much take data out of Beacon Tower in any way you would like. Either you can hook up directly into one of our endpoints, and we just stream all the telemetry value that would be needed out. We could push it into another endpoint, or we can do nightly transfers, so depending on what's needed. All these APIs that we use to work with this and are available for our customers to use in different ways also. And just to highlight this, this is just a very basic application where we connect to one of our endpoints, and we get all these 7 devices just streaming data out continuously into this. So this would be one way of getting this into a SCADA system. Another part we haven't really touched on yet either, which is dependent on a bit how you want to build this setup, is of course you can also use Beacon Tower to actually control devices. And sometimes we want to go through the SCADA system to do that, so we only send recommendations to the SCADA system, and you take a decision what you do there. Or in some cases, actually, like for this control device that Alan mentioned, you would probably use Beacon Tower to actually control it, but we can get those commands from a SCADA system, for example. So we can act as a middleman there, or there's all kinds of setups depending on the environment and the setup we want. Just an example here, I will use another simulated device. Let me just put those beside each other. So in this example, we just put a valve having no other options than that we can control. If it's closed or open or something in between. And this is something that you of course then if we can control this way, you can you can retrofit it as mentioned before, and then keep control over it over a wireless protocol somehow. So if we set this manually now, but this could of course be set automatically if we would like. Yeah, we see it's just sending a property, which is how we want to set it, and it then reacts to that pretty much instantaneously, and then it moves up. And as Alan said, this of course be a possibility to control this daily. I mean, and not only by season that we might do today, but by controlling exactly how much we want to set today for having an optimized network. That is, I think that is. Did I miss anything, Jacob? Or I think that, I mean, there's of course more things to talk about in Beacon Tower, but I think we'll probably cut it short there.
Yes, I don't think you missed anything. Just to sum it up, so what we have tried to inspire you guys with is a way to conduct these projects where you have different kind of sensors that you might want to test off. So let's say you want to try hydrostate, then say you want to try something from Intertek or a third other supplier of sensors, then that is completely possible with Beacon Tower, and then you get the data inside Beacon Tower and connect it to those different sensors, and then you can, as Michael has said, try to normalize these data and work with them, and then send them to the SCADA system if you also want to try that part of the project. And then you can use SIA Connect to get those data to the SCADA system, or the other way around, to get the data from the SCADA system to Beacon Tower if you want to combine those the SCADA data with the sensor data outside of the SCADA systems or the OT zone, in order to make presentations or reporting, or to make the control of the different sensors and actuators outside of the OT zone. So see this as some inspiration of how to get started within this area and to test off different ways to work inside this area, and see it as a very much as a flexible way that does not lock you into any certain vendor. This is lightweight. This is open data models, open APIs, and in short, a way to do this very agile, and also to give you some sort of idea of the kind of work that has been done in order to do these kind of activities. I think we can say that it's a matter of a few days work to get the integration to the SCADA systems together with SIA Connect, to get the data from the Agerkrantz sensors has also been quite easy. Not even days of work, but hours of work, I would say, from our side, to understand how Agerkrantz's hydrostate sensors are delivering data and in which format. So it has been quite easy. And also another point that we have maybe not touched upon is that the way that Albertslund has gone through this project and wish to go through this project is also to use the hydrostate sensors as a mobile sensor kit, so that they move the sensors to different test zones in order to identify where the lowest differential pressure is, and then to in those points install the sensors permanently, so that they can control the pump pressures automatically. But there's no reason to have the differential pressure sensors where it's not the lowest differential pressure. So in a way to locate that, that's also a way to do it in this project.